Hi everyone, this is the first video for day 2, week 3. The format for the videos are going to change slightly because I'm having some technical issues with the way I was doing the videos before. Okay, so these are the notes that you already find in your Google Classroom, which I have uploaded, and I'm going to just use these notes. Similar triangles, that's something we've learned before. Recall that two triangles are similar if all their angles are the same. Or actually, it's enough for two angles to be the same because the third angle then is automatically the same. And what happens when triangles are similar is that corresponding sides have the same ratio. For example, here, triangle ABC and DEF or DFE are similar because the angles sort of correspond, the 100, 100, 40, 40, 60, 60. And if you take the ratio of AC to DE, AB to DF, and BC to EF, they should come out to be the same number. Then the next thing we learned about was right triangles. And there was the specific example that we looked at before, which is nested right triangles. Now these I have drawn to scale. So what's the setup here? The triangle ABC is similar to triangle ADE. Why is that? Well, first of all, they both have 90 degrees. Secondly, they share angle A, so two angles are equal, which automatically guarantees that this third angle, angle C and angle E, are going to be equal. Now I'm going to use the theta variable that I introduced in day 1 video. That's a variable we fix for angles. And then I have these certain lengths here. So you can do this as an activity yourself where you can draw them to scale. So you see AB is 3 centimeters, 3, 4, 5, 6. AD is 6 centimeters. BC is 2 centimeters and ED is, or DE is 4 centimeters. So what we have is BC over AB is 2 over 3, and DE over AD is 4 over 6, which is also 2 over 3. That's not surprising because the triangles are similar. With this construction, you can also then measure AC, which is roughly 3.6 centimeters, and AE, which is 1, 2, 3, 4, 5, 6, 7.2 centimeters roughly. And then in your example, whatever triangle you construct, try and find these ratios. So here BC over AC, BC is 2 divided by 3.6. DE over AE is 4 divided by 7.2. AB over AC, let's see, AB is 3, AC is 3.6, and AD over AE is 6 over 7.2. Plug that into the calculator. 2 over 3.6, 2 divided by 3.6 comes out to 0.55. 4 divided by 7.2 also comes out to 0.55. 3 divided by 3.6 comes out to 0.83. And 6 divided by 7.2 comes out to 0.83. Again, nothing surprising as yet because these triangles are similar, which means we expect the sides to be in the same ratio. Okay, so here's some additional observation from the calculation and construction we just did. If you have a right triangle with the same angle theta, the ratio of the sides remain unchanged if the sides are changed proportionately. What does that mean? Look at this theta here and the two triangles ABC and ADE. They are two triangles with different side lengths but the same angle theta, and when you have that, the ratio of the sides of the triangle remain the same. Now this motivates us to give special names to these ratios. These ratios are called trigonometric ratios. Trigonometric ratios just means ratios of sides of triangle. And they are given specific names. Before we learn the names, let's learn to identify the sides of a right triangle. One that you already know is that the side opposite to the 90 degrees is called the hypotenuse. And previously we have referred to the other two sides as the legs of the triangle because that's what it stands on. Now, for the purposes of this week's material and for trigonometry, we need to be more specific about the names of the legs. And we have to identify an angle that we are interested in. Let's say I choose angle B and I call it theta. Then BC is hypotenuse, we already know that. The side AC is said to be opposite because it's opposite to theta. So if you look at theta and you're facing outward from theta, the side that is opposite to theta is AC, and that's called opposite. And the remaining side AB, it's adjacent to theta, so adjacent to theta. Now you may see that BC is also adjacent to theta, but we already have a special name for BC. It's the hypotenuse. So when we say adjacent, we refer to the other adjacent side, the one that is not the hypotenuse. For example, here I've labeled some sides and angles. Let's name them. Now the first one is really easy. So let's say I make a table here, hypotenuse. Now the hypotenuse is the easiest to identify. In this triangle, hypotenuse is the side A. This triangle, the hypotenuse is side Q. And in this triangle, the hypotenuse is side X. Again, hypotenuse is opposite to the 90 degrees. It's the side that's facing 90 degrees. What about opposite angle? Remember, opposite is with respect to the angle. So what's opposite theta in the first one is B. What's opposite theta in the second one is R. And what's opposite theta in the third one is Y. And then the adjacent is just what remains. So here it's C, here it's P, and here it's Z. This is very important that you know how to identify opposite and adjacent, because the opposite and adjacent depends on which theta you choose. Right? For example, let's say I make the same figure here with the same labeling of the sides, but I change my theta from the left to the right angle. Then the hypotenuse remains the same, but now the opposite to theta is Z and the adjacent is X. The adjacent is Y. So these two switch around. So you have to be very careful about which angle you are talking about. Okay, the last topic for this video. If I give you a right triangle, try and figure out with the sides AB, BC and AC how many unique ratios can be formed. Another way to think about it is, let's say I give you the numbers 3, 4 and 5. How many unique fractions can you make using two numbers at once? So let's see. If I use 3 and 4, I can make the fraction 3 over 4, or I can make the fraction 4 over 3. Using 4 and 5, I can make the fraction 4 over 5 and 5 over 4. Using 3 and 5, I can make the fraction 3 over 5 and 5 over 3. That's it. There's no more fractions that I can make. So if you look here, there are 6 possible fractions. Now if you were to do this generally, using the three sides AB, BC and AC, you could say I can have a fraction AB over AC. I can have its reciprocal, AC over AB. Then I can have BC over AC. I can have its reciprocal, AC over BC. Then I can have BC over AB and its reciprocal, AB over BC. So 6 fractions. And those are going to be the name of our trigonometric ratios. So these names are sine, cosine, tangent, cotangent, secant and cosecant. And these are, so the sine is defined as BC over AC, AB over AC, BC over AB. Now there is an acronym that you can use to remember this. How this acronym is constructed is you take this first letter. So you have sine is S, cosine is C, tangent is T. Then you look at the ratio. Sine is opposite over hypotenuse, so O and H. Cosine is adjacent over hypotenuse, so A and H. And tangent is opposite over adjacent, so O and A. And the acronym is SOHCAHTOA. So if you unpack the acronym, what you get is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then for the remaining three, you can observe that there's a reciprocal relation. So these are reciprocal. And then cosine and secant are reciprocal. And finally, sine and cosecant are reciprocal. So these are just names that we give for convenience, because it turns out that if triangles have the same angle, then these ratios are constant. So solving for one triangle solves for all possible triangles. Okay, that's it for this video. The next video we're going to look at some examples, how to find these ratios, and learn more about the ratios.